Now let's look at some examples of how we would use the alternating series test. And we'll start off with a alternating series here. Let's say this is n plus 1, like this. Okay, now, whenever we want to determine if a series converges, a lot of times, the best thing to do is start off applying the nth term test. Because if we can determine that this thing diverges right away, we don't need to go any further. So we apply the nth term test. So I say the limit as n goes to infinity of 1 over n plus 1. And that, of course, is equal to 0. So we can't rule out convergence. So this is one of the conditions that need to be met when we do the alternating series test. So that condition is met. Then what we want to do is determine, does this thing get smaller and smaller with each term? In other words, we have 1 over 1 plus 1 plus, well, the next term would be 1 over 2 plus 1. The next term would be 1 over 3 plus 1, as we just keep putting in values for n. And notice it does. The terms get smaller and smaller. See? So both conditions are met. Each term is getting progressively smaller than the previous, and it passes this nth term test. So yes, this series right here converges. It's an alternating series, so it converges. So an alternating series that has those two qualities, the limit is 0, and it's decreasing. When those two conditions are met, we can just say yes, by the alternating series test, that series converges. Now let's look at a little more challenging one. Let's suppose that we've got the series n goes from 1 to infinity. Let's make this minus 1, and then we've got 2n over 4n squared minus 3. Okay. Now, first thing I want to do is I want to make sure it passes this test. This limit has to be 0. And yeah, the bottom power is bigger than the top. And so as n goes to infinity, yeah, that's 0. So check, that's done. But we also want to determine, are the terms getting smaller and smaller and smaller? Now, they don't always have to be getting smaller and smaller and smaller, like, for example, at the beginning. But after you get to a certain point, this thing needs to be getting progressively smaller. In other words, there's a point out there where the terms of this series get smaller and smaller and smaller forevermore. Okay? So that's what we want to do. We want to find out, is there a point at which this thing is strictly decreasing? The terms are getting smaller and smaller. Well, one of the things we can do to check that out, and you can look at it and you can say, yeah, that's happening. I can tell just by looking at it. But you could look at the continuous function, replace the n's with x's, and just open up a little calculus on it. Right? We've got f of x equals 2x over 4x squared minus 3. Just look at this continuous function and see if that function is decreasing or increasing, or what's going on with it. So let's take the derivative. Derivative of the top is 2 times the bottom, minus the derivative of the bottom, which is 8x times the top, all over the bottom squared. Now, remember, when we want to know if a function is increasing or decreasing, we take the derivative of that function. Where the derivative is positive, the function is increasing. Where it's negative, the function is decreasing. So I've taken the derivative here. Now let's see what we've got. We've got f prime of x is equal to 8x squared minus 6 minus 16x squared all over the bottom. And generally, remember, we're not going to multiply out the bottom. That's usually not going to get us where we want to go. So now dig what we have here. We have negative 8x squared minus 6 all over 4x squared minus 3 squared. Now, if you look at this, the bottom is always positive. 4x squared minus 3 squared, that's always positive because it's squared. The top is always negative. So this thing is always less than 0. Always. For all n. So, yes, indeed. So here's what we've got. We've got the two conditions are met. Condition, this condition here, plus the function is decreasing. Each term is smaller than the previous term. So by the alternating series, this one converges. This is how we use the alternating series. Now, some of them, you don't have to go through all this process. You know, if you've got this one, clearly it's getting smaller and smaller. 1 over n factorial, every time you put in a new n, you're getting something smaller. You know, as you go 1, 2, 3, all the values for n. So on this one, you can look at it immediately and say, okay, yeah, this is the alternating series test will tell me this thing converges. Now, so we use the alternating series to show convergence, but let's, I want to look at another series here. Let's suppose we've got this one. We've got -1 to the n, 1 over n. Now, this series right here converges by alternating series test. So this converges, period. It meets the two qualifications, therefore it converges. But think about this series. What if we put an absolute value around it? In other words, what if I do this? What if I say n equals 1 to infinity, absolute value, -1 to the n, 1 over n? What if I do that? Well, now that is going to be exactly the same as this series, because we're just taking off the negatives. That series right there diverges. Okay? That's a divergent harmonic series, right? It's a harmonic series, it diverges. You could use the integral test and show it, but if you just remember, that's a harmonic series, it diverges. So this thing converges, but if we take away the negative parts, the alternating parts, it doesn't converge. So this thing has conditional convergence. Okay, this thing converges conditionally. Now, let's look at another one here. Let's suppose that we've got this one, n equals 1 to infinity, -1 to the n, 1 over n factorial. That one. Now, that one converges by alternating series, definitely. And if we take the negative away, let's see what we've got. We just end up with this. Now that one also converges, and you can show that series converges by the direct comparison test. But this series also converges. Both of these converge. So what we say is this converges absolutely. So we could say converges absolutely. Absolutely. Okay. So when something converges, even when you take away the alternating component, if you, in other words, when you look at the absolute value of all that's inside that sum, and if that still converges, we say that converges absolutely.